Welcome to our lecture video in hydraulics with the topic Hydrodynamics, forces developed by moving fluids. And in this video, we will have the forces acting on flat plate. And we will solve the 3 sample problems presented in this handout. Now, here in these forces acting on flat plate, we have 2 cases. The first one is when the plate is not in motion or that is stationary. So we can see the velocity of the plate is 0 meter per second. Having the release of water here, the jet velocity V1, and then the force exerted by the jet, and then we have here the formula for stationary plate. The force of the jet is equal to rho AV squared. Also, F is equal to rho QV, and force is equal to Q gamma over G times V, where rho is the mass density of liquid. The A there is the area of jet, that is the actual area of jet. So there will be a given diameter of jet here, not the diameter of the nozzle, rather the diameter of the jet. And then gamma is the specific weight of liquid. G is the gravitational acceleration, and we will use there 9.81 meter per second squared. And then we have Q as the rate of flow. V, or that is V sub 1, is the velocity of the jet. So having V sub 1 here as the velocity of the jet. V2 as the velocity of plate or the vane. So as you can see here, this V2 here is the velocity of the plate or the vane. Then F is the force of the jet, and R is the resisting force here. So that is for case 1, stationary. How about when the plate is moving at a certain speed? So having V2 have its value, meaning the vane is moving. The plate or the vane is moving. The formula now for the force of the jet is equal to the rho times the area times the velocity of the jet minus the velocity of the vane, and this is in squared. Or we have the formula F is equal to the density of water or density of the liquid times Q, or the rate of flow, times the velocity of the jet minus the velocity of the vane. Then we have F is equal to Q gamma, or that is the unit weight or specific weight of the liquid, all over the acceleration of gravity times the velocity of the jet minus the velocity of the vane. Now here is a simple note as for our sign conventions. If the V1 and V2 have the same direction of, this is the direction of flow of the jet, and this is the direction of travel or the movement of the vane, then it says here it's V1 minus the positive V2. But if they are in opposite direction, so V1 is going to the right and V2 is going to the left, that means the sign for V2 is negative. So in this formula, we will then have it as V1 minus quantity negative V2. That's why it will turn into V1 plus V2. Okay, so let's use this in solving for the 3 examples here in our handout. So for number 1, a jet of water 25 millimeters in diameter and having a velocity of 7.5 meter per second strikes against a plate at right angles. Determine the force on the plate. Letter A, if the plate is stationary. B, if the plate is moving in the same direction as the jet at a speed of 3 meters per second. and see if the plate is moving towards the nozzle of a velocity of 4 meters per second. So, for the first one, if the plate is stationary, so A. So this is our plate. So this is our plate. So stationary, or that is V2 is equal to 0. So our V1, it says here, the jet of water has a velocity of 7.5 meter per second. So V1 here is 7.5 meter per second. And the plate V2 is equal to 0. So determine the force. So F, we will use the formula here. F is equal to rho AV velocity squared. So rho of water mentions there water. Density of water is 1000. The area of the jet is pi over 4. Diameter of the jet is 25 mm, or that is 0.025 meter squared. And then we have the velocity, and that is 7.5 squared. If it is stationary, we will be using the velocity of the jet. So F now here is equal to 1000 times pi over 4 times 0.025 squared times 7.5 squared. So 27.61, that is Newton. 27.61 Newton. Now how about letter B? If the plate is moving in the same direction as the jet at a speed of 3 meters per second. So that means the V2 here, so our V2 is equal to positive 3 meter per second. So same jet velocity, V1 is equal to 7.5, and then V2 is 3, that is in meter per second. So again, the formula here that we're going to use is F is equal to rho area V squared, rho of 1000 pi over 4.025 squared, and then since it's already moving, so what we get from the formula, so our formula is V1 minus V2. So V1 minus V2 squared. So this is 7.5 for V1 minus V2 of 3, that is squared. So what is now the value of F? 7.5 minus 3 squared. So 9.94 Newton. So 9.94 Newton force. Now letter C. If the plate is moving towards the nozzle at a velocity of 4 meters per second. So the plate is moving opposite V1. So this is our V1 of 7.5 meter per second. This is our V2 of 4 meter per second, negative. So V2 is equal to negative 4 meter per second. And from our formula, F is equal to rho A V1 minus V2 squared. F now is equal to 1,000 times pi over 4 diameter squared. Then V1 of 7.5 minus negative 4 meter per second. So what is now the value of F? So this becomes negative 4. So 64.92. 64.92 Newton. So that's example number 1. So let's go to example number 2. A 50 mm diameter horizontal jet of water strikes a flat plate as shown. Determine the jet velocity if an 80 Newton horizontal force is required to permit the plate, letter A, to move at a constant speed of 2 meter per second to the right. B, stationary. C, to move at a constant speed of 2 meter per second to the left. So, for letter A, so the plate is to move 2 meter per second to the right. So, determine the jet velocity. So, there's no jet velocity here, but we are given V2, moving. So, V2 is 2 meter per second moving to the right. And what else? Given a horizontal force of 80 Newton. So, horizontal force of 80 Newton, F. So, compute for V1. So, V2 here is positive 2 meter per second, indicating that it is moving to the right. This is case number 2. Since the plate is moving, we're using the formula F is equal to density times V times area, then V1 minus V2 squared. So, given F as 80 Newton equals 1,000 over pi over 4. V1 is unknown. V2 is 2 squared. So, what is the value for V1? So, you're going to use the shift solve function. 80 equals 1,000 times shift pi over 4 times alpha, or that is alpha x minus 2 squared. Shift solve. So, we have here, we forgot the diameter. The diameter, 50 mm. So, the 50 mm means 0.05 squared. So, there is 0.05 squared there. So, shift solve. So, the positive one there is x is equal to 8.38. So, 8.38 meter per second. Then, for letter B, it says there, the plate is stationary. So, the plate is stationary. So, that means V2 is equal to 0. V2 is 0. So, we're looking for V1. And then, the plate here, V2 is equal to 0. Given, again, F is equal to 80 Newton. So, from the formula, F is equal to the density area V1 minus V2 squared. So, given F is equal to 80, density is 1,000, area is pi over 4, diameter of 0.05 squared. V1 minus 0 squared. So what is V1? So that is square root of, so 80 times 4 all over 1000 times shift pi times 0.05 squared. So that is 6.38 meter per second. Next, letter C. Letter C means, it says here, to move at a constant speed of 2 meter per second to the left. That is opposite the direction of the jet. So V2 of negative 2 meter per second. So V1 is unknown, V2 is negative 2 meter per second, given F is equal to 80 Newton. Then we will use the same formula. F is equal to the density times the area, V1 minus V2 squared. So 80 equals 1000 pi over 4.05 squared, V1 minus V2 squared. So 80, so our V2, by the way, our V2 is negative. So that means V1 minus negative 2 squared. So what is V1? So that is 80 alpha equals 1000 times shift pi over 4 diameter of 0.05 squared alpha x plus 2 squared. Shift solve. So 4.38. V1 is 4.38 meter per second. So that is example number 2. So we have here the last example number 3. So in the figure, the 75 millimeter diameter orifices at the sides of the two tanks are at the same elevation and with the same geometrical and hydraulic properties. So it's talking about the orifice here of the two tanks. They have the same elevation, they have the same geometrical and hydraulic properties. A plate is placed against the orifice of the first tank, so this plate here. Assume that the tanks are close enough that the effect of gravity on the jet is not considered. Neglect losses and weight of the plate. Compute the, letter A, rate of discharge of tank 2 if H2 is equal to 4 meters and C is equal to 0.60. Then B, dynamic force of the issuing jet from the second tank. So the dynamic force F. C, height H1 if the dynamic force of the issuing jet from the second tank is just enough to hold the plate placed against the orifice of the first tank. So let's solve first for letter A. Rate of discharge, we're looking for the Q. We're looking for Q here. Rate of discharge of tank 2 if H2 is equal to 4 meters and C is equal to 0.60. So that is Q2. Now for letter A, since we're talking about orifices here, that is Q2 is equal to CA, given the C there. So CA square root of 2GH. So this formula, if you recall, so this is equal to C of 0.60 the area of the orifice of diameter 75 mm. So that is pi over 4, diameter 0.075 squared, and square root of twice of the gravitational acceleration, and the h here is the height of water from the water level up to the orifice. So that is 4. So we now have Q2. So we have now the value for Q2 as 0.6 times shift pi over 4 times 0.075 squared, square root of 2 times 9.81 times 4. So that is 0.023 cubic meters per second. 0.023 cubic meter per second. So that is for letter A. Now B, dynamic force of the issuing jet from the second tank. So it's looking for the dynamic force F. So when we say dynamic force, that involves the velocity. So B is equal to F is equal to Q gamma G, and that is in multiply with the velocity. So let's see if we are consistent with the sign here. Q is cubic meter per second, gamma is in kilonewton per cubic meter, velocity is meter per second, all over gravitational acceleration is meter per second squared. So we will cancel out. Seconds squared, and then what else? We can cancel here the cubic meter and the meter. What's left is kilonewton. Therefore, it's consistent that we can get the value of F using this way. Now, remembering that Q is equal to AV, because here there is no given velocity. So QAV, we can get or derive formula Q gamma over G. Velocity is Q over A. So that means F now is equal to Q squared gamma over G A. So we can now use this. F is equal to Q. Q is 0.023 squared, gamma of water, so water, 9.81, all over the acceleration of gravity, 9.81, the area of the jet, of the orifice. So pi over 4. So the given area here, the given diameter here is the orifice. So the area of the orifice here is 0.075 squared. Pi over 4 times 0.075 squared. So what's the dynamic force here? 0.023 squared times 9.81 all over. So we can cancel 9.81 already. Times 4 shift pi times 0.075 squared. So that is F is equal to 0.12 kilonewton. So that's for letter B, the dynamic force. C, height H1 if the dynamic force of the issuing jet from the second tank is just enough to hold the plate placed against the orifice of the first tank. So what could we observe here? If the F here is the dynamic force, how about the force here? What do we call the force here that is inside the tank? It's called the static force. So the force outside is the dynamic force and the force inside is the static force, and they are equal. So let's name this as F1, or the force of the tank 1, then F2, the dynamic force from the tank 2. So for letter C, static force. So the static force that is inside the tank, what's the formula for that static force again that we used to solve there in the fluid mechanics? That is F is equal to gamma bar HA. So that's the static force. And for the dynamic force, that is the F equals Q squared gamma that we were able to derive a while ago. So this one here. So since F1 is equal to F2, in order to have this plate stationary there, it won't be moving. So Q gamma that is gamma HA H bar A is equal to Q squared gamma G over A. So we can cancel out here the gamma. By the way, is this consistent? If we review the unit, that is kilonewton per cubic meter, and then meter squared. Cancel this one, so we have kilonewton, consistent. So meter. Now since we have Q, let's return the velocity. So AV, QAV. So this H here, bar H, is actually the H1. A equals, the Q there is A V squared all over GA. So H1 is equal to area squared B squared all over G A squared. Cancel here the A squared. And knowing that V for the orifice there is 2G H2. So H1 is equal to the V squared there is square root of 2G H2 squared over G. And we can cancel out the square there. So H1 is equal to, cancel, so it becomes 2GH2 over G, cancel G. So H1 is 2H2. H1 is 2 times 4 meters. So H1 is equal to 8 meters. So H1 is equal to 8 meters. So that's example number 3. So that ends our video.